Okay, what is concurrency? That's essentially about in your program running um, multiple things at the same time. Now, back in the day, you could only kind of do one thing at a time. Back in the day, you had the command line, like if you were pretty much the dominant personal, small computer was the PC, the Microsoft. It was DOS, and so you had basically a big black screen, and you could type one thing and run one thing, and that was kind of pretty much it. Um, Nowadays, you have a bazillion things running at once. So just even in this, I mean, I have the PowerPoint running. QuickTime is also recording this. At the same time, I have NetBeans running. I have, there are lots of things running, and we've gotten used to the fact that on the computer there can be multiple things running at the same time, and it seems like they're all running simultaneously. Um, Now, back in the day, even when there was just a uh, single CPU, it would kind of look like that. It would look like there were multiple things running at the same time, even though there was only one processor. So now how it does that is kind of a little beyond the scope of things. But what concurrent, so those are processes, and those are actually fairly heavyweight things, because if think about what it takes to run each one of these different processes. So what does it take to run PowerPoint in this mode? I mean, it had to load a file somewhere. It had to execute whatever code it does to refresh the screen. It's and then in NetBeans, a program could actually be running at the same time. So those processes are fairly heavyweight. So what does concurrency mean? The concurrency means things running at the same time. So what is a thread? So what a thread is so called because it's a lightweight process. In other words, it doesn't have all of the extra um, overhead of a process, but it's very thin, very lightweight. And so the idea is that in the program there are multiple things running at the same time that could also potentially access the same code. Now, we're not going to get into too deeply into that issue because it's a fairly complex one and a little bit beyond the scope of this class. Um, Java was pretty much, if not the first, one of the first languages in which the capability of doing that was built in, the capability of running these multiple threads at the same time. The ability to do that had been around. But if you were running in a different language, then the only way to do it would be to have a separate library. So if you're running C, for example, you could do this kind of thing, but you had to use a library that set up all the stuff for it. So Java built it into the language. And the problem is they ran into a lot of problems, though, because, and unfortunately, the book comes at this from the level of the sausage factory. And the thing is that doing this at the low level, which is unfortunately how the book approaches it, is just pretty much a pain. So what you're going to see here is a little bit more of a high level and a more reliable, a more robust, kind of a better way of doing it. And that involves things called executors and these things called callables. So we'll get into all that. So basically, you should be able to create one of these runnable things. So what's runnable? Runnable is the interface. Thread is the concrete class. The book, there are kind of two ways of creating one of these. One is to implement the runnable interface. The other is to extend the thread class. you should never extend the thread class. It just turned out that was just a bad idea. So always implement runnable. And the thing is that just even from a practical standpoint, because Java has single inheritance, that is, once I subclass something, I only get one choice. So if I subclass thread, I can't subclass anything else. In almost all other cases, all the use cases I've had, I want to subclass another class, not thread. So how much work do you have to do? Like why subclass something instead of implementing an interface? If I implement an interface, that means I have to write a whole bunch of methods. Why? Because implementing an interface means signing a contract to implement a set of methods. If I subclass something, then that means that I get everything in the superclass for free. The problem is that whether I subclass thread or implement runnable, there's only one method I need to write, and I need to write it in every case. So if I subclass thread, I need to override the run method. If I implement the runnable class, I need to write a run method. Same amount of work either way, except I kind of tie myself in a knot if I subclass thread. So don't subclass thread, always implement runnable. So basically each thread is a separate computation unit running at the same time. And so unlike humans, computers these days are very good at multitasking. Humans we're terrible at multitasking. People claim they're good at multitasking. When they've done studies on it, they discover that they're not. They say they're good, but they're as soon as you try to do more than one thing, your performance degrades. Not so much with computers. I mean, there actually is a little bit of performance degrading. Why? Because of the overhead of what a thread involves. Actually, in today's computing, these days, these computers are pretty amazing. They have multiple cores, both physical cores and logical cores. So what that means is that the actual overhead of running multiple threads is minuscule, and we'll actually see an example of that. So the idea is that I can have multiple things running at the same time. You can share the data and the code with all the other threads in the same program. That's one of the things that distinguish threads from processes. Like if I'm running a process on the computer, it doesn't, like PowerPoint isn't interacting with NetBeans. I mean, they're completely separate. They're kind of walled off from each other. Threads, on the other hand, are very lightweight. And actually, in every program you've been running, there have been actually two threads that you may or may not have been aware of. Okay, every Java program has a main thread. When you start the Java virtual machine and it enters main, it creates what's called a main thread. That's the main thread of execution. But there's also another thread that's running silently in the background for the garbage collector. We've touched on what does the garbage collector do? When the virtual machine realizes that an object has been created, which means there's a bit of memory that has been put away to store this object. At some point, all references to the object have disappeared, to that particular object. And so if you don't do anything, then that piece of memory is going to kind of stay allocated, and eventually you're going to kind of run out. That's what's called a memory leak. What the garbage collector does, it's this little thread running in the background, and every now and then when nothing else is going on, the garbage collector thread wakes up, it goes looking for these bits of garbage that aren't used anymore, and it frees up that memory for these objects that aren't used anymore. So that's all been running in the background since the beginning. And if you've looked at when you run a program that's thrown an exception, and you look at the error message, it will often say exception in thread main. You remember seeing that? Yeah. What that means is that the main thread has thrown the exception. In other words, that was the thread that was actually running. Now, the thing is that now users, and this is the new thing, users we can create our own threads. Okay, now why do that? Well, the biggest use case that I've had, there are two main reasons for uses for that. One is what we're going to encounter shortly is that we're running a graphical user interface program. There's a specific thread for displaying the graphics on the screen, and that's a separate thread. If you're also, if you're running a graphical interface that also has to do a very time-intensive task, then you want to make sure that that runs in a different thread than the graphics thread. Because if you run, so let's say I had a very computational intensive task that I'm running with a user interface. If I run on the same thread as the one that's displaying my graphics, then until that's finished with that long task, the graphics don't have an opportunity to refresh the screen. What does that look like to a user? It means that your application is locked up and won't respond. Has that ever happened to you? You're running an application, all of a sudden it locks up. Okay, well, now there are things that have gone wrong there, but if you're writing a program and you have a long computational task that doesn't involve refreshing the screen, and you accidentally run it in the graphics thread, then what you've done is you've locked the screen up for your user. In other words, you've kind of created that problem for him. So that's one use case. The second one that I've encountered in programs that I've worked is that there are situations in which you can kind of run things simultaneously. In other words, like one application in a simulation, I'll literally be running tens of thousands of replications of a particular simulation, sometimes with different parameters. If I run those all in one thread, then each one has to wait for the other one to finish. And it turns out that if I can kind of and write them in a way that they run parallel, then I can, in this case, I will typically run up to 16 ones simultaneously, and the reason I do that is because usually, or at least the computers I run on have 16 logical cores, so they don't there isn't a lot of swapping going on. So, and it literally will save the computational time by the number of threads, and we'll see an example of that. Okay, so that's the why. Like, why are we, so there may be times you're thinking, okay, why is he talking about this to us? Why do we have to kind of learn this? So hopefully you have some idea of why this is important. Okay, so there are kind of two. There's the thread class, and there's the runnable interface. The runnable interface is very lightweight. It has one single method called run. The thread class, which implements runnable, also has a run, but the run that thread has isn't anything that you'd ever want to use, so you always have to override it. So even though you can do it differently, what you should always do is instantiate a runnable, write your class to implement runnable, and then when you want to actually run it, okay, one way, we're going to see two ways of doing this. Okay, one way to use the thread is to pass the runnable to the thread class, and what that does is the thread will then use your runnable instead of its run. And then what you do is, instead of calling run, you call a method of thread called start. And then what happens in start, as we'll see, is that start will actually start the thread and immediately return. So this can be a little confusing. So it'll start the thread. So the thread is off running in its own little thing, but then it immediately returns and starts executing what the next lines of code are. So in other words, the control continues past the start. Now, in the old days, what we typically wanted to do is once a thread kind of grabs things, to be a good citizen, it needs to kind of do a little bit of work and then say, okay, I'm kind of done. At the low level, there were methods that you would called yield and then wait and notify and stuff like that. That's all way too low level, it turns out, and way too easy to kind of screw up. So one way was to kind of work for a little while and then go to sleep. Thread had a sleep method that kind of puts and it's actually a static method. You would put the current thread to sleep for a little while. Turns out that was one of these good ideas that wasn't so good. So don't do that. Instead, they fixed it with a method called time unit, and that's what we use instead. Unfortunately, for some reason, the book didn't talk about that. So the execution happens it seems to occur simultaneously. Now, sometimes it literally occurs simultaneously, and a lot depends on what else is running on your computer, because all of these are competing for your CPU's resources. But even if you have more things running on one logical core, what it does is it kind of swaps things in and out with something called the thread scheduler. Okay, so here's a real simple example. The book had one about tortoises and hares, which is also kind of cute. But this is kind of this is the one that so you'll have two examples, one in the book and one here. So this liftoff class, we have a countdown that starts at 10, and then it implements runnable. And the run method is going to sleep for 1 second and then decrement countdown from 10. And then when it reaches 0, you're going to return from run. So how do you know when the thread is done? It's when you return from the run method. Okay? And okay, so let's see what that is about. Okay, so if you do a pull, you should be able to see this. Okay, so here's the liftoff method. Now I'm using this other little pattern that we had. Each one is going to have its own ID, and so we can kind of figure out who's who, because we're going to have a bunch of these running around. And the pattern that I like for this is to have a static int. That's and it can either start at 0 if you're okay with the 0-based thing. If you don't like that, you can start it at 1. And then every time you instantiate one, you set its instance variable to whatever the current one is, and then increment the static one. So we've done that before, but that's sort of separate from the whole thing here. Here's the run method. So when the run happens, I'm going to have a while loop. So while my countdown, which where is it? What the heck was I thinking? Okay, this. How did that happen? I would mark this down. So I'm gonna. One of my little bugaboos is always, when possible, initialize your instance variables in the constructor, not the way it was done here. I don't know what I was thinking. I screw up myself. So okay. So countdown is going to start at 10, and while it's bigger than 0, I'm going to print, now normally you don't kind of want to do this, but because this is just an example and I wanted to show where each one was, and the only the only ability to do that is kind of within here. I probably should have done a logger, but anyway. So each iteration through the loop, I'm decrementing by 1, and now I'm going to sleep for 1 second. So instead of thread sleep, this is where I use the time unit. And what's nice about time unit is that, see, the thread sleep was for milliseconds, which, but like the time unit, I can I can sleep for days, hours, microseconds, milliseconds, minutes, nanoseconds, or seconds. So, and it's this kind of works with the threads a little nicer. The thread sleep turned out to be a problematic. Now, and these always throw an interrupted exception, because there are times when you can, it's like, in a way, it's like if a program kind of locks up, you can kind of blow it away. You can do similar things, but it requires a little bit of extra code. Okay, so basically that's really all it is. And the status is simply saying, okay, here's the current countdown. If it's bigger than 0, otherwise it's we're counting to a liftoff, whatever. Okay, so let's sort of here's how we can test this. So I can create one, and here I'm passing it. I'm instantiating a thread, but I'm passing it the runnable. So this is if we're using threads, that's the preferred way to do it. And I'm going to say, okay, I'm going to start the first one. And then here I'm going to start the second one. And then now, if you're kind of in the traditional mindset of kind of executing things one line at a time, what mentally we think, well, okay, each of these are going to do all their countdowns, and then when they're done, we're going to say we're all finished. That's what you would think, but that's not what you see. When we run this, notice that, okay, we started the first thread, we started the second thread, and then we printed all finished. Why was that? Well, because remember I said when you execute start, it immediately it starts a thread, but it immediately returns. So it started the thread, returned. Started the next thread, returned. And then printed all finished. So in a way, the program is lying to us. So we're going to say, okay, well, are we all finished? Blah, blah. Now here's the other thing to notice. Notice I started the one that was 0 first. And so what was happening here? So the 0th one had a countdown of 10, and then it printed the 1, because that was the next one. But look what happened next. Next, it did the 1. And then, so what's happening here? There are 2 threads that are currently running, and the thread scheduler in the virtual machine, if there's a thread that has finished with its sleep, and they're both sleeping for exactly the same amount of time, it picks one. Which one does it pick? We have no idea, and we have no control. Well, there's a little bit of control. We can try to give it priority, but basically we can kind of beg and plead, but at the end of the day, the thread scheduler has its own thing. So there's no, you would think it would always go 0, 1, 0, 1, 0, 1, but it doesn't. It's random. It's arbitrary. Okay, so how can we kind of get around this thing where they're all finished? Okay, so we say we're all finished, but we're not finished. So how can we do that? Well, we can, this is a little bit lower level than what is best, but okay, here I'm going to create 10 of these threads, same thread, same liftoff. I'm going to start them all. But then each thread has a method called join. And what join says is that don't move past this point until that thread is finished. So here I've created these 10 threads. Okay, this is the same thing. Started them all, so they're off and running. But now I'm saying, okay, now for each of these threads, I'm going to invoke join. And what that's going to do is that's going to sort of stop the right here. And in this case, because I'm doing it for all 10 threads, we're going to stop right here. And then all done is going to happen after it's finished. Now here's the other thing. Now notice that for this, it typically takes about 10 seconds to run through this, because we start at 10, count down to 0, 10, 9, so 10 seconds is about what it would take to run one of these. But then notice that it actually took 11 seconds. What was 11? 10, 9, maybe 11, I don't know, 10 or 11 seconds. I had, this damn zero-based thing. So you would have thought it would take 20 or 22 seconds to do this, but it only took 11 seconds. Okay, why? Because they were running simultaneously. So that's the performance speed up. And then here we're running 10 of them. So let's run 10 of them. Okay, now notice that we have before join, but we're not saying all done. And then now here they get even more mixed up. So even in the first one, we go 5, 7, 1, 2, 9, 4, 3, 8. So the thread scheduler, again, it's just doing its own thing. And then finally, they all lifted off. And it also took 11 seconds. So it took pretty much the same amount of time to run 10 of them as to run one of them or two of them. I mean, now there is sort of because of finite resources. I mean, I can't, if I wanted to run 1,000,000, it would probably take more than 11 seconds. But now, do you see? In other words, I have performed 10 times the amount of work in the same amount of time. So if I can write my programs in such a way that this parallelism can happen, then all of a sudden I've had a huge I've done multiples of the amount of work in the same amount of time, and generally that's what you want to do. Okay, so again, so when we actually start on the thread, we return the thread schedule. It chooses the next one at random. I mean, there's no true randomness going on in computers, of course. How does it choose? I mean, I have no idea. You'd have to kind of somehow find the source code for the virtual machine and find the scheduler piece and sort of figure that out. I've never done that. I don't know anybody who has, other than the really smart programmers who write these things. So that's way beyond my pay grade. So for threads, we have join to do that if we're working with threads. Now the thing is that and after kind of a lot of, I mean, there are literally books written on how to kind of figure all this stuff out. There are issues with synchronization. Like in this particular case, we were running completely separate. There was no shared code, basically. Although, well, they were all executing the same logic, but they were doing it in different objects. But there are situations where different threads will be accessing the same block of code, and that can be problematic, and it can kind of screw things up. That's where you kind of get into synchronization and things like that. The book kind of talks about it. That's for our purposes, that's something where, I mean, if you're writing programs that are going to be doing that, then kind of do that. For what we're doing in this class, we're not going to kind of go that deeply into it. However, it turns out that it is actually slightly better to use a slightly higher level of abstraction on this, and that's where these executors come in. I mean, literally after years of people kind of banging their heads on keyboards to make these threads do what they want, they finally said, hey, let's have something that kind of does a little better job of this. And that's where they came up with these sort of executor things. And they're, There are basically there are three versions of them. The first version is called a cached thread pool. And what that does is what you do is you create your runnable things and you pass it to them, and what the cached thread pool does is it'll, as long as you keep giving it new runnables, it just keeps executing them. In other words, this is like a collection, like a set or a list. You keep adding and it keeps kind of going, if you add 1 million, it'll gleefully do 1 million. And your computer will lock up, of course. But what it does is it sort of under the hood, what it does is it creates this pool of threads, and then every time it goes to execute one of your runnables, it kind of pulls from the pool, and then when it's done with it, it puts it back in the pool. See, the problem with using it at the thread level is once we're done with the thread, we can't really reuse it as we're doing it there. Or it is possible, but you have to write a lot of code, and then the code that they were written, these patterns emerge, and that's where the pools kind of end. Now, this is like an array list type of thing. I can add as much as I want, and then the thing is that okay, now maybe I don't want to. Maybe I want to kind of restrict the number of simultaneous threads that are running, because if I try to put too many in, it'll kind of grind everything to a halt. So that's where a fixed thread pool comes in. I say, well, I want to run no more than 10 threads simultaneously. So if I give it 100, it will run 10 at a time, and as each one finishes, it'll grab the next one, and then be finished only when it's finished all the hundreds. And at the extreme end of that, a single thread pool, I'll say, okay, it's basically a fixed thread pool with the size of 1, and that'll run them sequentially to completion. Not terribly useful for, if you're running threads to improve your execution. Running a fixed thread pool kind of ignores why you're doing this. In other words, if I were to run what we just did with a fixed thread pool, it would take 10 times the 10 seconds. It would take 100 seconds to run all of them because it would run them sequentially.
So what would an application
Well, the way that I've used it is that I've set up a situation, say, where I will literally have 100 or so simulations that I want to run simultaneously. And I don't want to run them. In fact, what I do, the code that I have, it kind of actually looks at the platform you're running, figures out how many logical cores you have, and creates that many threads. So typically it's been 16. So if I give it 100 simulations, it will run them 16 at a time. That's been my main use of it. And I do, now I could run more, but if the reason I do, like what I noticed is in doing some experimentation, I noticed that the virtual machine was assigning the different threads to the separate cores, and that was the most efficient way to run it. So what it does is it reads the platform and says, okay, if you have 32 cores, then it'll run 32 at a time. But if I try to run them all at once, it'll just grind everything to a halt. So that's so fixed thread pool is cached thread pool is something you want to use only if you're sure you're not going to overwhelm the machine. Okay, so the executors have two methods that are actually there are 3 methods that we use, but one terribly named method and 2 very well named methods. So here's some examples of that. So right, well here's one example. Here's the single thread pool. And let's do it with our liftoff people. So So I instantiate, and the way to instantiate them is because there's some stuff it needs to do behind the scenes. Instead of instantiating it, we get them with what's called a factory method. So we've seen, I think, at least another example of this. So instead of saying new executor, it's called an executor service, is kind of the interface for this. And I just say new single thread executor. That'll give me a single thread executor. So here if I'm running I'll run 5 threads. Now here's executors execute. So that's equivalent to the thread start method. This is the this actually, when I first started working with this totally confused me. Executors shutdown. I mean, if you have a method called shutdown, what does that tell you it's going to do? It's going to shut it down. It doesn't shut it down. What it means is, it says to the executor, I'm not going to give you any more threads or any more runnables. So shutdown just means I'm going to shut down the open door. In other words, execute says I'm giving you another one. Shutdown says there are no more coming, but it doesn't shut it down. That again, badly named. Okay, but then just like with the thread start, things will just kind of keep going, and that of course can be a little problematic. So here's another well-named method. It's called await termination. So now instead of if you remember, for join, I had to join every single thread that I had. If one got through, then it would slip out slip through. But here, because I've done everything in the executors, if I say await termination, very well named. Join isn't so well named, by the way, but await termination. I mean, that's So what this says is await termination. Now the only trick here is I need to give it a timeout. In other words, this says I'm going to wait for 10 minutes, which hopefully it's not going to take 10 minutes. But I do have programs that sometimes run for days, so I have to. All right, so it's going to wait for 10 minutes. If things haven't finished by 10 minutes, then it's going to just kind of go on. Okay, so let's see how that works. So now this is a single thread. Now notice that now I've given it 5 of these things, and it's only processing the one. And move on to the next one. Okay, so this kind of, and then notice that it hasn't. Well, okay, I didn't. Did I say anything? I say all finished. No, all finished hasn't happened yet. So, okay, so that's. So what's the point of this if I'm not going to exploit the multitasking? Well, let's see, where is it? Okay, so here's a fixed thread pool. So same thing. So let's say I'll have 5 threads. So this says I want my executor to run 5 threads at once, and then I'm actually going to create 6 threads to just show you what happens. And then same deal. I'm going to await termination. I'm going to say all finished only when we move past that. Okay, so now, if you notice that there are 5 of these running, 0 through 4, and they all lift off, but then here's the 5th one, or the 6th one. So I said I'm going to run 5 threads, but I gave it 6 runnables, and so it ran the first 4, and then by the time it finished those, then it ran the last one. Whereas if I run it in a cache thread pool, no matter how many I give it, no matter how many I give it, it's just going to do them all. Same deal. And notice that they're still getting all mixed up there. Okay, so this is the preferred way to be running these threads. Like like that. Now, and then after, now, then people started complaining even more about the limitation of this. What's the limitation? The limitation is that this run method does not return anything. So when I'm finished with the run, it doesn't give me any information. And so the only way to kind of get information out is I would have to, I'd have to kind of set some variables in here, and then when it was done, kind of go and ask them about it. And then after doing that, a lot of people were kind of complaining about that, say, hey, there must be a better way to do that. I want a return value. Give me something on this. And so that's where they came up with this idea, and we'll have to pick it up next week. If I want a return value, then they came up with two different very useful interfaces, one called callable and one called future. So what the callable does is it has a call method that returns actually an arbitrary object. So that object can be, I've used this to return things from like a number to a string. I've returned lists of things. I've returned a JSON file. You can return any kind of object. And you get those with something called a future. So that, so in other words, this allows you to write programs where you're kind of running stuff, producing some kind of output, giving the output to these futures, and then the future can kind of do something with it. So we'll pick up on that next week, and then we're going to kind of move on to creating graphical user interfaces, because that's kind of the cooler thing.